In March of 2025, the James Webb Space Telescope captured something that had never been seen before: a direct image of auroras blazing across the mid-latitudes of Neptune. At the same moment, the same telescope recorded a temperature drop in Neptune's upper atmosphere so steep that it had nearly halved compared to what Voyager 2 measured back in 1989. Two surprising readings arriving at the same time, and scientists are still working out what they mean. Neptune is the most remote planet in our solar system. It orbits the Sun at a distance of roughly 4.5 billion kilometers, which is about 30 times farther from the Sun than Earth is. That distance alone makes it extraordinarily difficult to study. From Earth's surface, Neptune appears as little more than a faint blue-green dot, even through a powerful telescope. The Sun appears about 900 times dimmer from Neptune than it does from Earth. And yet, despite that faint illumination, Neptune is home to some of the most violent and dynamic atmospheric activity in the entire solar system. What makes that fact so puzzling is that Neptune's neighbor Uranus, a nearly identical planet in terms of size and chemical makeup, sits relatively quiet by comparison. Wind speeds on Uranus can reach around 900 kilometers per hour, which is impressive. But Neptune's equatorial winds have been measured at over 2,160 kilometers per hour, nearly approaching the speed of sound. The difference between two chemically similar planets separated by just a few billion kilometers in the outer solar system raises a question that scientists have been trying to answer for decades. Why is Neptune so dramatically more active than Uranus? Part of the answer appears to come from inside the planet itself. Before we go any further, if you're enjoying this, consider subscribing. It really helps us keep creating videos like this. Now let's get back to the video. Unlike Uranus, which barely radiates any excess heat at all, Neptune emits significantly more energy from its interior than it receives from the sunday. This internal heat source drives convection, the circulation of warm material rising, and cooler material sinking, which in turn fuels the wind and storm systems visible in the atmosphere. The leading explanation for why Uranus lacks this internal heat is that a massive collision with an Earth-sized object may have occurred billions of years ago, disrupting Uranus and bleeding away its primordial heat reserves. Neptune, apparently, escaped that fate. But that internal heat alone cannot fully explain every aspect of Neptune's behavior. The recent James Webb observations have introduced new questions that add considerable complexity to what scientists already thought they knew. To understand why those images matter so much, it helps to trace the full history of what we know about Neptune and how we came to know it. Neptune holds a unique distinction among all the planets in our solar system. It is the only planet that was discovered not through direct observation, but through mathematical reasoning alone. Every other planet visible from Earth was found because someone looked up at the sky and noticed an unfamiliar point of light moving against the background of stars. Neptune was found entirely differently. The story begins in the early 1800s, when astronomers were studying the orbit of Uranus, the planet just inside Neptune's orbit. Uranus had been discovered in 1781 by William Herschel, and by the 1830s and 40s, astronomers had accumulated enough observations to track how it moved through the sky. There was a problem. Uranus was not moving where it was supposed to be. Its actual path differed from the path predicted by Newtonian gravitational theory, and the deviations were not random. They followed a consistent pattern, suggesting a systematic gravitational influence pulling at the planet from beyond. In France, an astronomer and mathematician named Urbain Jean-Joseph Leverrier studied this problem with meticulous care. His reasoning was logical and bold. If Uranus was being pulled off course by gravity, then there must be a source of that gravity, an unseen planet orbiting further from the Sun, tugging at Uranus as it moved. Leverrier calculated where that planet would have to be in order to produce exactly the deviations that had been observed in Uranus's path. He arrived at a specific location in the night sky and announced his prediction. On the night of September 23, 1846, Leverrier's colleague, Johann Gottfried Galle, pointed a telescope at the exact position Leverrier had specified and found Neptune within a single hour of searching. The planet was within 1 degree of the predicted location, an astonishing confirmation of the power of mathematical physics, and one of the most dramatic moments in the history of astronomy. Just a few days later, observers discovered Triton, Neptune's largest moon, orbiting the newly found planet. Since that discovery, Neptune has been one of the hardest objects in the solar system to study closely. A round trip in communication alone, signals traveling at the speed of light, takes over 8 hours. Sending a spacecraft there requires extraordinary patience. Using the current generation of rocket technology, even a direct trajectory to Neptune would take around 13 years. The only mission that has ever visited Neptune, Voyager 2, managed the journey in 12 years by using a sequence of gravitational assists from Jupiter, Saturn, and Uranus, a maneuver that required a precise planetary alignment that repeats only once every 175 years. Voyager 2 departed the Uranus system on January 25, 1986, after photographing that planet and its moons. It captured one final image of Uranus from about 1 million kilometers as it departed. For 3 more years, it crossed the void toward Neptune, traveling at 54,000 kilometers per hour. When it finally arrived in August of 1989, it passed within 5,000 kilometers of Neptune's North Pole, the closest any spacecraft has flown past any planetary body during a flyby mission. That encounter transformed our understanding of Neptune in a matter of days. Voyager 2 confirmed that Neptune has a ring system. It revealed previously unknown moons. It directly measured the wind speeds in Neptune's atmosphere for the first time, and it captured images of storms large enough to swallow the entire Earth. The most famous of these was the Great Dark Spot, a colossal counterclockwise rotating vortex roughly the size of Earth that sat in Neptune's southern hemisphere. Winds at the edges of the Great Dark Spot were measured at up to 2,400 kilometers per hour, the fastest wind speed ever recorded in the solar system. A smaller storm, simply called the Small Dark Spot, also appeared in the southern hemisphere. As Voyager 2 drew closer, this smaller storm was seen to change color from dark to light, a behavior that had no immediate explanation. A NASA analyst named Ken Bollinger, reflecting on the data arriving in real time in 1989, described the experience by saying that every day brought something new that no one had ever seen before, with changes happening constantly and very fast. That observation captured something fundamental about Neptune. Unlike Jupiter's Great Red Spot, which has persisted for centuries, Neptune's storms appear to form, evolve, and vanish on timescales of just a few years. When the Hubble Space Telescope was trained on Neptune in 1999, both dark spots had completely disappeared. New storms had taken their place, and those too have been seen to come and go in the decades since. A storm observed in 2015 appeared to be on a similar timescale of a few years. The behavior suggests that Neptune's atmosphere might be organized into bands, similar to Jupiter but far less defined and far fewer in number. Where adjacent bands flow at different speeds, they can generate the boundary conditions that allow a vortex to form. Once such a storm develops, it can drift across the planet, but when it moves away from whatever energy source was sustaining it, it gradually weakens and fades. Hubble remains one of the few instruments capable of monitoring these changes over time, largely because Neptune's storms are extremely difficult to observe in most wavelengths of light. Hubble's ability to observe in the ultraviolet makes it particularly valuable for studying both Neptune and Uranus from Earth orbit. Beyond the storms, Neptune's interior holds additional surprises. The planet is classified as an ice giant, a category it shares with Uranus. That term does not mean ice in the everyday sense of frozen water. It refers to a chemical composition dominated by compounds containing hydrogen and oxygen, as well as nitrogen and carbon, in a hot, dense fluid state. Neptune's atmosphere is made up of roughly 80% hydrogen, with methane accounting for about 19% of the remainder. Methane absorbs red wavelengths of sunlight and reflects blue wavelengths, which is why Neptune appears the deep azure color it does in photographs. Deeper inside, beneath the visible atmosphere, is a thick mantle of water, ammonia, and methane in a fluid or icy state surrounding a rocky inner core. The conditions inside this planet are extreme. Near the boundary between the core and the mantle, pressure is estimated to reach around 7 million times the atmospheric pressure at Earth's surface. Under conditions like those, methane molecules can be torn apart, and the carbon atoms may be subjected to pressures high enough to form diamonds. Scientists believe that rather than solid diamond crystals in the conventional sense, what may exist is a liquid carbon ocean with solid diamond formations floating and sinking through it, essentially diamonds, precipitating like hailstones through the interior of the planet. This hypothesis was long considered speculative, but laboratory experiments using high-powered lasers to recreate extreme pressures inside materials have begun to test it. While no direct measurement from inside Neptune is possible, the physics of carbon under extreme pressure does support the idea that diamond rain could be a real phenomenon occurring inside ice giants. Neptune's magnetic field adds another layer of strangeness. Most planetary magnetic fields are roughly aligned with the planet's rotational axis. Earth's magnetic north is tilted only about 11 degrees from its geographic north pole. Neptune's magnetic field is tilted 47 degrees from its rotational axis. This extreme misalignment means the magnetic field is wildly asymmetric around the planet, which affects how charged particles from the Sun interact with Neptune's magnetosphere. When Voyager 2 discovered the same extreme tilt in Uranus's magnetic field, the first assumption was that it had something to do with Uranus's unusual 98-degree axial tilt. The planet orbits the Sun, essentially lying on its side. The discovery of the same offset in Neptune, which has a much more ordinary axial tilt of 28 degrees, ruled that explanation out. The current leading hypothesis is that the magnetic fields of both ice giants are not generated in the planetary core the way Earth's field is generated, but rather in the electrically conducting fluid mantle. Alternatively, the mantle might be deflecting a core-generated field, distorting it away from alignment. Either way, the physics of magnetism inside ice giants appears to be fundamentally different from what happens inside rocky planets or gas giants. Auroras exist on Neptune, as they do on every planet in the solar system with a significant magnetic field. But Neptune's auroras are extraordinarily faint. The Sun's influence weakens with the square of distance, so at 30 astronomical units from the Sun, the solar wind particles reaching Neptune carry far less energy than at Earth's distance. That means fewer charged particles enter the magnetosphere, and the resulting light emissions are weaker. Additionally, because the magnetic field is so tilted, Neptune's auroras do not cluster around the polar regions the way Earth's auroras do. Instead, they appear at mid-latitudes. For decades, Neptune's auroras remained unobserved, and their precise nature was largely theoretical. That changed in March of 2025, when the James Webb Space Telescope captured direct images of Neptune's auroras glowing in near-infrared light across the planet's mid-latitudes. The images were striking shimmering structures extending across Neptune in ways that had only been predicted but never seen. This was the first direct visual confirmation of auroras on Neptune. At the same time that Webb captured those aurora images, it also detected something unexpected in Neptune's upper atmosphere. The temperature had dropped dramatically compared to what Voyager 2 measured in 1989. In the decades between Voyager's flyby and Webb's observations, Neptune's upper atmospheric temperature appeared to have nearly halved. This was a significant and puzzling change for a planet that sits so far from the Sun that many astronomers expected it to be relatively stable on human timescales. What is driving that temperature drop remains an open question. Some of the potential explanations involve changes in the chemistry of Neptune's upper atmosphere over time, possibly related to how certain gases absorb or release energy. Others involve changes in solar activity over the same period. Neptune does experience seasons. Its axial tilt of 28 degrees is similar to Earth's and to Mars's, meaning that like both of those planets, it has a spring, summer, autumn, and winter. The key difference is that Neptune's year is 165 Earth years long. Each season lasts roughly 40 years. The southern hemisphere is currently experiencing spring, meaning it is receiving gradually increasing amounts of sunlight compared to previous decades. This seasonal change has observable effects. During southern spring, methane that was frozen in the troposphere gradually sublimates into the stratosphere, brightening that part of the planet. The southern hemisphere has been visibly brighter in observations taken over recent decades. The increase in sunlight reaching the southern hemisphere warms that region by roughly 10 degrees Celsius compared to the rest of the planet, which sounds modest, but is actually a significant temperature difference on a planet where the baseline atmospheric temperature is around negative 201 degrees Celsius. Whether the temperature drop detected by Webb is related to these seasonal dynamics or to something else entirely is not yet known. The detection of the aurora at the same time complicates the picture further, since auroral activity and upper atmospheric temperature are connected in ways that are not fully understood even for Earth. The colder temperatures may actually suppress auroral brightness, which could help explain why Neptune's auroras went undetected for so long, even though they were presumably always present. Neptune's ring system adds further intrigue to the planet's story. The rings were suspected as early as the 1960s and 70s, when astronomers measuring how Neptune's disk dimmed background stars during close passes noticed what appeared to be partial structures blocking starlight. But the evidence was inconsistent. The dimming would occur on one side of the planet but not the other, which led some scientists to propose that Neptune might have ring arcs rather than complete rings. Voyager 2 confirmed that both interpretations were partly correct. Neptune has 5 named rings, all of which are extremely dark and faint. The innermost is the Gay Ring, a broad and diffuse band about 2,000 kilometers wide. Moving outward is the Leverrier Ring, narrower at about 113 kilometers, but noticeably brighter. Connected to the Leverrier Ring is the Lassell Ring, a very faint band spanning about 4,000 kilometers. On the outer edge of the Lassell Ring sits the Arago Ring, slightly brighter and less than 100 kilometers across. Finally, the outermost and most closely studied is the Adams Ring, only about 35 kilometers wide, but one of the brightest in Neptune's system. What makes the Adams Ring particularly interesting is the presence of arcs regions within the ring where material has clumped into concentrated bands, rather than being spread uniformly around the orbit. These arcs have been observed to be relatively stable since their discovery in 1980, which is scientifically puzzling. Rings are not static structures. The particles within them collide and drift, and any concentration of material should spread out over time due to the differential orbital speeds of particles at slightly different distances from the planet. The fact that the arcs have remained stable for decades suggests that something is actively confining them, possibly the gravitational influence of one of Neptune's small inner moons acting as a shepherd, corralling the particles into a dense concentration. But the exact mechanism remains an area of active research. Of all of Neptune's moons, the one that commands the most scientific interest is Triton. It is enormous by comparison to the other moons in Neptune's system, containing 99.5% of all the mass in orbit around Neptune. In terms of size, Triton is the 7th largest moon in the entire solar system and is larger than Pluto. If Triton were orbiting the Sun independently, rather than orbiting Neptune, it would be classified as a dwarf planet. But what sets Triton apart from every other large moon in the solar system is not its size, it is its orbit. Triton orbits Neptune in the wrong direction. Every other large spherical moon in the solar system orbits its parent planet in the same direction that the planet rotates. Triton orbits clockwise around Neptune, while Neptune rotates counterclockwise. Moreover, Triton's orbit is inclined about 130 degrees relative to Neptune's equatorial plane. These orbital characteristics are the defining signature of a captured object, a body that did not form alongside Neptune in the early solar system, but was instead drawn in from elsewhere. The leading hypothesis for Triton's capture involves binary dynamics. Early in the solar system's history, Triton likely orbited the Sun as part of a binary pair, two objects gravitationally bound to each other, similar to the Pluto-Charon system. When this binary pair passed close to Neptune, the gravitational interaction would have torn the pair apart, flinging one object away on a new orbit around the Sun, while the other Triton lost enough momentum to be captured into orbit around Neptune. This process would not have required a direct collision, and is consistent with the physics of three-body gravitational interactions. Strong evidence for this origin comes from New Horizons, which flew past Pluto in 2015. The probe's measurements revealed that Triton and Pluto share a nearly identical chemical composition. Both have surfaces dominated by nitrogen ice, with mixed-in ices of water and carbon dioxide. Both have thin nitrogen atmospheres, and both have similar densities. This points to a shared origin in the Kuiper Belt, the region of the outer solar system beyond Neptune, populated by icy bodies left over from the formation of the planets. Triton's surface looks young. It has very few impact craters, which means it is being continuously resurfaced by geological activity rather than accumulating the cratering record that ancient, inactive surfaces display. Under Triton's icy exterior is thought to be a rocky and metallic interior, and between the ice crust and the rocky core, there may be a subsurface liquid water ocean kept warm by the radioactive decay of elements in the rocky interior. A similar situation is thought to exist under the surfaces of Europa, Jupiter's moon, and Enceladus, Saturn's moon, both of which have become high-priority targets in the search for conditions that could support life. Cryovolcanism is active on Triton today. Liquid water from the interior erupts onto the surface in a process analogous to volcanic activity on Earth, but using water rather than molten rock. When this liquid water reaches the freezing cold surface of Triton, it solidifies almost immediately, creating relatively smooth young plains that continuously overwrite older terrain. Identified on the surface are solidified lava lakes, flat plains surrounded by raised walls, as well as calderas, which are the collapse depressions found at the summit of volcanoes. These features confirm that Triton's geology is actively driven by interior heat. Voyager 2 also captured images of smaller eruptions on Triton plume-like features, reaching up to 8 kilometers in height. These may not originate directly from the interior ocean. A mechanism called the solid greenhouse effect may be responsible. Triton's surface is layered with transparent ice, sitting atop darker organic compounds called tholins. Sunlight passes through the transparent ice and is absorbed by the darker tholins beneath, which then sublimate the ice in a small pocket, building up pressure until the overlying ice gives way and the gas erupts upward, carrying some of the darker material with it. This process is very similar to what has been observed at the poles of Mars, where carbon dioxide ice and dark deposits interact to produce analogous eruptions. The tholins on Triton's surface are produced when methane in the atmosphere, or on the surface, reacts with ultraviolet radiation from the sunday. Tholins are organic compounds. They contain the kinds of carbon-based molecules that form the chemical foundation of biology. Their presence does not indicate life, but it does indicate that Triton has the raw chemical ingredients. If Triton's subsurface ocean contains dissolved minerals from the rocky interior, brought to the surface by cryovolcanic eruptions and cycled through tidal heating and chemical reactions, then the conditions for prebiotic chemistry could theoretically exist in the liquid layer beneath the ice. Triton has a thin atmosphere, composed mainly of nitrogen, with a surface pressure of about 0.014 millibars, roughly equivalent to the atmosphere at 80 kilometers altitude on Earth. This is barely an atmosphere at all, but it is dense enough to support weather. Voyager 2's images show actual cloud structures in Triton's lower atmosphere, reaching up to about 8 kilometers above the surface. The direction of deposits left by plume eruptions all point the same way, indicating the presence of prevailing winds in certain regions of the Moon. The atmosphere has actually thickened slightly since Voyager 2's observations, likely because rising temperatures in the southern hemisphere are sublimating nitrogen ice from the surface into the gas phase, a seasonal change similar in principle to what happens on Pluto. Beyond Triton, Neptune has 13 other known moons. The second largest is Proteus, an irregularly shaped body about 400 kilometers across. Normally, objects at that size become spherical under their own gravity, but Proteus has retained an irregular shape, likely because past collisions created massive craters that distorted its form before the interior could reflow. One of those collisions was probably energetic enough to produce fragments, and one of those fragments may now be visible as Hippocamp, a small irregular moon about 35 kilometers long that orbits close to Proteus and was discovered by Hubble in 2013. Several of Neptune's outer moons orbit on extremely elongated and inclined paths that take years to complete a single circuit around the planet. These are almost certainly captured objects, likely drawn into their current orbits by gravitational perturbations from Triton following its own capture into the Neptune system. The outermost known moons of Neptune, Psamathe, and Neso take about 25 years each to complete a single orbit. They are currently the most distant known satellites of any planet in the solar system. Neptune's reach extends even further than its moons. In 2020, a trans-Neptunian object designated 2020 VN40 was found to be in an orbital resonance with Neptune, completing exactly one orbit around the Sun for every 10 orbits Neptune completes. Given that Neptune's year is 165 Earth years, this object takes 1,650 Earth years per orbit. Its orbit is highly inclined, but the precise ratio of the resonance shows that it is gravitationally locked in a long-term dance with Neptune, its trajectory shaped by the planet's gravity over billions of years. This is not unusual. Neptune exerts a powerful organizing influence over the outer solar system. Many objects in the Kuiper Belt are locked in similar resonances with Neptune, orbiting in precise ratios relative to Neptune's orbital period. Pluto itself is in a 3-to-2 resonance with Neptune, completing 2 orbits for every 3 that Neptune completes. This relationship keeps Pluto's orbit safely synchronized with Neptune's, ensuring the two bodies never actually come close to each other despite the fact that Pluto's orbit crosses inside Neptune's at certain points. Given all that is now known about Neptune, what stands out is how much still remains unknown. We have visited this planet once, briefly, more than 3 decades ago. Voyager 2 flew through the Neptune system at speed, collecting what data it could during a single pass lasting only a few hours in close proximity. Everything else we know has been pieced together from ground-based observations and occasional measurements by telescopes in Earth orbit. The James Webb Space Telescope is changing that situation in ways that were not anticipated even a few years ago. Webb's near-infrared sensitivity is revealing structures and phenomena that no previous instrument could detect from Earth's distance. The aurora images from March 2025 were the first of what will likely be many discoveries from Webb's ongoing observations of Neptune. The temperature readings from those same observations have already altered scientists' understanding of how Neptune's upper atmosphere has evolved over recent decades, raising questions about the timescales and mechanisms behind large-scale changes in ice giant atmospheres. Several scientific teams have proposed dedicated Neptune missions in the years since the last Planetary Science Decadal Survey, which is the comprehensive document that guides priorities in solar system exploration for a 10-year period. A mission to an ice giant, either Neptune or Uranus, was identified as one of the highest scientific priorities for the next decade. The case for such a mission rests on how poorly understood the ice giant class of planets is, and on the growing evidence that ice giant-sized worlds may be among the most common types of planets in the galaxy. Observations of exoplanets, planets orbiting other stars, have found that many solar systems contain worlds in the size range between Earth and Jupiter, with Neptune-sized objects representing a significant portion of that population. Understanding how ice giants form, how their interiors are structured, how their magnetic fields work, and how their ring and moon systems evolve has become a matter of broader astronomical interest, not just solar system science. There is also a proposed Chinese mission to Neptune that was being considered for a launch as early as 2033. If such a mission proceeds, it would mark the first time since 1989 that a spacecraft had traveled to Neptune and would arrive with instruments far more capable than anything Voyager 2 carried. An orbiter mission rather than a simple flyby would transform the level of detail available across all of Neptune's systems: the atmosphere, the rings, the magnetic field, the moons. The questions such a mission could address are well defined. What is driving the dramatic temperature changes in Neptune's upper atmosphere? Are the temperature trends observed by Webb part of a long-term cooling episode? Or are they part of a seasonal cycle? What is the exact mechanism behind the ring arcs in the atom's ring? What is the current state of Triton, and how has its surface changed since Voyager 2's images? Does Triton have a subsurface ocean? And if so, does it have the chemistry that could support simple biological processes? Understanding Neptune also means understanding the history of the solar system. The current model of how the solar system formed, known as the Nice model, and its various successors, proposes that the giant planets did not form in their current locations. Early in the solar system's history, the planets migrated significantly. Jupiter may have moved inward toward the Sun before being pushed back out. Saturn, Uranus, and Neptune all shifted in their orbital positions as they interacted gravitationally with the disk of gas and dust from which they were forming. Neptune, according to this model, migrated substantially outward, and as it did so, it swept through the Kuiper Belt, scattering objects outward, capturing others like Triton, and locking many more into the orbital resonances that are still visible today. The pattern of orbital resonances in the outer solar system, the captured moons of Neptune, and the distribution of Kuiper Belt objects all record the history of planetary migration that shaped the solar system into its present configuration. Neptune is not merely an interesting planet in isolation. It is a key to reading the history of how the entire solar system was assembled. And yet, despite all of this, Neptune remains largely unexplored. Of all the planets, it has received the least scientific attention, the fewest dedicated observations, and only a single brief visit from a spacecraft in the entire history of spaceflight. Everything we know about Neptune's great dark spots, its diamond rain interiors, its tilted magnetic field, its active cryovolcanic moon, its stable ring arcs, its seasonal temperature swings, and now, its newly imaged auroras has been assembled from a handful of telescopic campaigns, and the data from one spacecraft that flew through the system in a matter of hours in the summer of 1989. The recent James Webb images are a reminder that even from over 4 billion kilometers away, Neptune still has the capacity to surprise. A temperature drop that halved the upper atmospheric reading. Auroras burning at mid-latitudes, where the magnetic field arcs away from the poles. Neither of these observations was predicted. Both of them are telling scientists that their models of Neptune's behavior are missing something important. That is exactly where science is most productive, at the edge of what is understood. Neptune, the outermost planet, the one found by mathematics before it was found by a telescope, the one visited once and never revisited, the one with diamond rain in its interior, and a captured dwarf planet for a moon, remains one of the most scientifically rich and poorly understood objects in the solar system. What Webb has shown is that even passive observations from Earth's orbit can still uncover phenomena that reshape the questions being asked about Neptune. An orbital mission, with instruments trained on the planet continuously for years rather than hours, would almost certainly reveal things that are currently unimaginable. Until such a mission flies, scientists will continue extracting what they can from the occasional images and data collected by telescopes on the ground and in Earth orbit, piecing together one observation at a time. The full story of the final planet. To truly appreciate what Webb's observations mean and why scientists were surprised by them, it helps to understand what the James Webb Space Telescope is and how it differs from every instrument that came before it. Webb is not simply a larger version of the Hubble Space Telescope. It operates on fundamentally different physical principles, observes in different wavelengths of light, and sits at a fundamentally different location in space. Hubble orbits Earth at an altitude of about 540 kilometers, relatively close by astronomical standards. Webb orbits the Sun at a point about 1.5 million kilometers from Earth, at a location known as the second Lagrange point, or LUT. At this distance, Webb always faces away from the sun and is shielded from solar radiation by a large 5-layer sunshield roughly the size of a tennis court. This sunshield allows Webb's instruments to cool to temperatures near negative 233 degrees Celsius, close to absolute zero, which is essential for detecting infrared light. Hubble primarily observes invisible light and ultraviolet, with some infrared capability. Webb was designed primarily as an infrared telescope. Infrared light is heat radiation. It is the kind of light emitted by warm objects, rather than the kind emitted by hot, luminous stars. Infrared observation allows astronomers to see through dust clouds that block visible light, to detect the faint thermal signatures of distant planets and their atmospheres, and to observe very distant galaxies whose light has been redshifted by the expansion of the universe out of the visible range and into the infrared. For observing objects in our own solar system, Webb's infrared capability means it can detect chemical signatures, thermal emission, and atmospheric dynamics that are invisible to instruments operating in the visible spectrum. Neptune's auroras, for example, emit light primarily in the near-infrared through emission from trihydrogen cation, a molecular ion of hydrogen with the chemical formula H3+, written with the charge as a superscript. This molecule produces a distinctive signature when excited by auroral processes, and it emits primarily in the near-infrared at wavelengths that Webb is exceptionally well suited to detect. Hubble, working primarily in visible and ultraviolet, could not easily detect these emissions. The detection of trihydrogen cation auroras on Neptune is scientifically significant beyond just being a first-ever image. This molecule was first detected in auroras on Jupiter, where it was found in 1988. It was subsequently detected on Saturn and Uranus. Neptune was the last of the gas and ice giants to have its auroral emissions confirmed in this way. The detection completes a pattern across the outer solar system, allowing comparative studies of how auroral processes work in different magnetic environments. What makes Neptune's case different from Jupiter and Saturn is the extreme tilt of the magnetic field. On Jupiter and Saturn, the magnetic field is much more closely aligned with the rotational axis, so auroral emissions concentrate near the poles in oval-shaped bands, similar to Earth's aurora borealis and aurora australis. On Neptune, with the field tilted nearly 50 degrees from the rotational axis, the auroral ovals are offset dramatically from the poles and appear at much lower latitudes. Webb's 2025 images showed these mid-latitude auroral structures for the first time, directly confirming what theoretical models had been predicting for decades, based on the magnetic field geometry measured by Voyager 2. The temperature data from the same observations requires more explanation to understand why it is so surprising. Planetary upper atmospheres called thermospheres are heated primarily by two processes. One is solar extreme ultraviolet radiation, which is absorbed by gas molecules at high altitude. The other is energy deposited by auroral processes, which accelerate charged particles that then collide with atmospheric molecules and heat them. On Earth, these two processes together keep the thermosphere at temperatures ranging from roughly 500 to 2000 degrees Celsius, depending on solar activity. On Neptune, the expected thermospheric temperature, based on the level of solar radiation at that distance, was very low. Even accounting for auroral heating, theoretical models predicted a much colder thermosphere than was actually measured by Voyager 2 in 1989. Voyager found temperatures in the upper atmosphere far higher than models predicted, a discrepancy that became known as the energy crisis of the outer solar system, because the same problem appeared at Uranus, and to a lesser extent at Jupiter and Saturn as well. Where was the extra energy coming from? One hypothesis involves gravity waves, waves of compression and rarefaction propagating upward through the atmosphere from storm activity lower down, depositing energy in the thermosphere. Another involves the dissipation of tidal effects from large moons. A third invokes horizontal mixing of energy from regions of stronger auroral activity into regions of weaker heating. None of these explanations has been fully confirmed. What Webb's 2025 measurements revealed is that Neptune's thermosphere is now significantly colder than it was when Voyager 2 measured it. This might seem to reduce the mystery of the energy crisis if the atmosphere is cooling. Perhaps the extra energy is simply dissipating. But it actually creates new questions. Why is the thermosphere cooling so dramatically? Over what timescale did the cooling begin? Is it related to the seasonal changes in Neptune's southern hemisphere, or to changes in solar activity over the same period, or to some internal process within the atmosphere itself? Neptune's distance from the Sun means that seasonal effects play out very slowly. A change in solar angle that would take 3 months on Earth takes 40 years on Neptune. The southern hemisphere has been moving through spring, receiving gradually increasing sunlight. If increased sunlight is somehow driving the cooling of the upper atmosphere, perhaps through a feedback mechanism involving methane chemistry or auroral suppression, that would be an unusual and counterintuitive result that would require careful modeling to explain. Some researchers have pointed out that increased methane in the stratosphere during southern spring could affect how energy flows through the atmosphere. Methane is a greenhouse gas in one sense, but it also absorbs and re-emits radiation in ways that can change the energy balance at different altitudes. The release of frozen methane from the troposphere into the stratosphere during warming is itself a complex process. And if the stratosphere is loading with methane at the same time as the thermosphere is cooling, there may be a connection worth investigating. The auroral brightness observed by Webb may also carry information about the cooling. Auroras in the thermosphere are brighter when the thermosphere is warmer, because warmer gas molecules are more easily excited by the collisions caused by accelerated particles. A cooler thermosphere produces weaker auroral emission for the same particle flux. This means that Neptune's auroras could have been occurring at roughly the same intensity of particle precipitation for decades, but were simply too faint to detect earlier because the thermosphere had already begun cooling. The fact that Webb detected them in 2025 might mean not that the auroras suddenly became stronger, but that Webb is simply sensitive enough to detect them even in their weakened state. All of this points to a planet that is undergoing measurable change on human observable timescales. For outer solar system, objects that scientists often think of as static and slow-moving, that is a remarkable finding. The solar system's most distant planet is apparently shifting in ways that modern instruments can detect within a human lifetime. To understand how unusual Neptune is in the context of planetary science more broadly, it helps to compare it to the other classes of planets in our solar system. The 8 planets fall into 3 rough categories. The rocky terrestrial planets Mercury, Venus, Earth, and Mars are relatively small, dense, and made mostly of silicate rock and metal. The gas giants Jupiter and Saturn are enormous, contain mostly hydrogen and helium by mass, and have no solid surface. And then, there are the ice giants Uranus and Neptune, which are intermediate in size and have a fundamentally different chemical composition from the gas giants despite superficially resembling them. Ice giants are roughly 14 to 17 times the mass of Earth, compared to Jupiter's 318 Earth masses. Their atmospheres are dominated by hydrogen and helium like the gas giants, but a much larger fraction of their total mass is composed of water, ammonia, and methane. The ice is in a dense, hot, high-pressure fluid state deep in the interior. This layered structure, with a thick icy mantle surrounding a rocky core and topped by a hydrogen-helium atmosphere, is what defines the ice giant class. What makes ice giants particularly interesting from a planetary science perspective is that they appear to be the most common class of large planet in the galaxy. Surveys of exoplanets, planets around other stars, conducted by the Kepler Space Telescope, and subsequent missions have revealed that sub-Neptune and Neptune-sized worlds are extremely abundant. They appear in the census of known exoplanets far more often than gas giants or even Earth-sized rocky planets. This means that understanding the physics of Neptune, its atmosphere, its interior, its magnetic field, its formation history, is not just relevant to our own solar system. It is directly relevant to understanding the most common type of large planet in the observable universe. Yet Neptune is the class member we know least about. Jupiter has been orbited by the Galileo probe, which descended an atmospheric probe into the cloud layers in 1995, and the Juno spacecraft, which has been in orbit since 2016. Saturn was orbited by the Cassini spacecraft for 13 years, from 2004 to 2017, producing an extraordinarily detailed picture of the planet and its moons. Uranus has at least been proposed as a target for an orbital mission in the current Planetary Science Decadal Survey. Neptune has had no orbital mission and no confirmed plans for one. The gap in our knowledge is stark. Voyager 2's flyby gave us the equivalent of a snapshot, a series of measurements taken during a brief period in one small season of Neptune's 165-year orbit. If Voyager 2 had flown through the Jupiter system in the same way, scientists would have no idea that Jupiter's auroras are dynamic and variable, that its magnetic field rotates with the planet in complex ways, or that its atmospheric bands are unstable over timescales of years. It was only continuous observation from orbit that revealed those facts about Jupiter. Neptune remains at the level of a single snapshot. What would an orbital mission to Neptune be able to measure that a flyby cannot? The list is long. An orbiter could monitor how Neptune's storm systems evolve over a period of years, tracking individual vortices from their formation to their dissipation, and mapping the band structure that may drive them. It could measure the composition of Neptune's atmosphere at multiple altitudes and latitudes, identifying chemical gradients and mapping the vertical structure that controls how energy moves through the planet. It could map the magnetic field in 3 dimensions and at multiple points in Neptune's orbit, revealing how the field changes over time and whether it undergoes polarity reversals like Earth's. An orbiter could also conduct dedicated flybys of Neptune's moons, particularly Triton. A close pass by Triton with modern instruments could search for active plumes, map the chemical composition of the surface in detail, and look for evidence of subsurface liquid using radio waves or gravitational measurements. If a subsurface ocean exists on Triton and is warm enough to sustain liquid water, the gravitational signature of that fluid layer would be detectable by precise measurements of how Triton's gravity deforms the spacecraft's trajectory. Similar techniques have been used to confirm the subsurface oceans of Europa and Enceladus. The rings of Neptune could also be studied in far greater detail from orbit. Images taken from different angles, in different wavelengths, and at different points along the orbit would reveal the 3-dimensional structure of the rings and allow scientists to track how individual ring particles move and how the arc structures in the Adam's ring maintain themselves over time. The interaction between ring particles and the small inner shepherd moons could be directly observed rather than inferred from ground-based data. An atmospheric probe, dropped into Neptune's atmosphere like the Galileo probe at Jupiter, could measure temperature, pressure, wind speed, and chemical composition as a function of depth, directly probing the layered structure that scientists can currently only infer from indirect observations. Such a probe would likely survive only a few hours before being crushed by the increasing pressure. But in that time, it could sample a region of the atmosphere that no instrument has ever directly measured. The technical challenges of such a mission are substantial, but not insurmountable. The travel time to Neptune is the most significant constraint. Even with optimized trajectories using gravitational assists from Jupiter and Saturn, a Neptune orbiter would require roughly 12 to 15 years to reach its destination. That means a mission launched in 2035 might not enter orbit around Neptune until the late 2040s. Planning, building, testing, and launching the spacecraft, given the lead times typical in planetary science, would require decisions made now, in the mid-2020s. To materialize as a working spacecraft at Neptune in the 2040s, power is another challenge. Solar panels are impractical at Neptune's distance because sunlight is simply too faint to generate useful electricity at 30 astronomical units from the Sunday. Missions to the outer solar system rely on radioisotope thermoelectric generators, which convert heat from the radioactive decay of plutonium-238 into electricity. These are reliable and long-lived, but the supply of plutonium-238 is limited, and producing more is a slow and expensive process. Space agencies have been working to increase production, and new radioisotope generators have been under development, but the availability of power sources is a real constraint on how many outer solar system missions can be launched within any given decade. Communication is also a challenge. At Neptune's distance, a radio signal traveling at the speed of light takes about 4 hours and 15 minutes to reach Earth on average, and up to 8 hours and 10 minutes near maximum separation. Commands sent from Earth take that long to arrive, and data returned from the spacecraft takes equally long to reach receivers. This means the spacecraft must be largely autonomous, capable of making decisions about its own operations without waiting hours for human input, and that downloading the full volume of data from complex observations requires careful scheduling over many months. Despite these challenges, both NASA and the European Space Agency have conducted detailed studies of Neptune mission concepts. One concept studied in depth is called Neptune Odyssey, which would combine an orbiter and an atmospheric probe into a single mission. The orbiter would spend at least 4 years in the Neptune system, with numerous targeted flybys of Triton and the other moons. The atmospheric probe would descend into Neptune's atmosphere and return data on the deep interior composition that no orbital instrument could access. Another concept focused specifically on Triton, proposing a dedicated orbiter for that moon. The case for a Triton mission rests on its potential as an ocean world. If Triton has a subsurface liquid water ocean, it joins a growing list of ocean worlds in the solar system: Europa, Enceladus, Titan, Ganymede, and possibly others, each of which is considered a candidate environment for life. A Triton orbiter could investigate this question directly and return data relevant to some of the most fundamental questions in astrobiology. The context of astrobiology is worth unpacking. The search for life beyond Earth is no longer focused solely on Mars or on habitable zone planets orbiting other stars. The discovery of active geysers on Enceladus, which contain water, organic compounds, and molecular hydrogen ingredients suggestive of chemical reactions that could power microbial life, dramatically expanded the definition of habitable environments in the solar system. The confirmation of a global subsurface ocean on Europa, kilometers deep and in contact with a rocky seafloor, made it one of the highest priority targets in astrobiology. Triton, with its rivers and lakes of liquid methane and a probable subsurface water ocean, is another target of intense interest. Triton fits naturally into this conversation. Its active cryovolcanism means that material from deep inside is regularly cycling to the surface, potentially bringing dissolved minerals and organic compounds from a subsurface ocean into contact with the surface environment. Its atmosphere, thin as it is, hosts chemical processes driven by ultraviolet radiation. Its surface tholins are complex organic molecules. None of this proves life is present, but the combination of a liquid water layer, chemical cycling, and organic chemistry is a combination that appears repeatedly on bodies scientists consider worth investigating in depth. The broader history of how we have come to understand the outer solar system over the past few decades is one of progressive surprise. Every mission to a new target in the outer solar system has returned findings that exceeded expectations. Pioneer 10 and 11 gave the first direct measurements of conditions in the outer solar system. Voyager 1 and 2 revealed an outer solar system that was geologically active in ways no one had anticipated, with active volcanoes on Io, a possible subsurface ocean under Europa's ice, and complex moon systems at Jupiter and Saturn that proved far richer than anything models had predicted. Cassini at Saturn found active geysers on Enceladus in 2005, discovered lakes and rivers of liquid hydrocarbons on Triton, and revealed that Saturn's rings are a dynamic and geologically young system rather than an ancient relic. New Horizons at Pluto found a world with towering ice mountains, vast nitrogen ice plains, a layered atmosphere, and possible subsurface liquid water, a world of extraordinary complexity that many scientists had expected to be a featureless frozen rock. The Juno mission at Jupiter revealed weather patterns that penetrate thousands of kilometers deep into the planet, and polar cyclone systems unlike anything seen on other planets. Neptune, by the logic of this consistent pattern, would almost certainly hold similar surprises for a dedicated mission. Its one and only visitor departed more than 3 decades ago. The planet's atmosphere has been changing in ways that can be detected even from Earth orbit. Its moon Triton is geologically active and chemically rich. Its ring arcs remain unexplained. Its magnetic field is anomalous. Its internal heat source is poorly constrained. Its thermosphere has cooled dramatically since the last in situ measurement. Every one of those open questions has an answer. The answers are in the data that a spacecraft in orbit around Neptune could collect. The science is waiting. The technology to conduct such a mission exists or is being developed. The decision of whether and when to send such a mission is one of scientific priority and institutional commitment questions about how resources are allocated among the many compelling targets in solar system exploration. In the meantime, Webb will continue to observe Neptune from its position at the second Lagrange point, about 1.5 million kilometers from Earth. Each new observation adds to a growing dataset of how Neptune changes over time. The 2025 aurora images and temperature data will be followed by further campaigns targeting different aspects of the planet. Scientists are already analyzing what the temperature measurements imply for models of thermospheric heating in ice giant atmospheres, and what the aurora images reveal about the geometry and intensity of particle precipitation in Neptune's magnetic field. Ground-based observatories, equipped with adaptive optics systems, which use deformable mirrors to compensate for the blurring effect of Earth's atmosphere, have also continued to contribute to Neptune studies. Large telescopes like the Very Large Telescope in Chile and the Keck Observatory in Hawaii can achieve angular resolutions sufficient to track large features in Neptune's cloud layers, monitor changes in the planet's brightness due to seasonal variations, and observe the moons under favorable conditions. The Atacama Large Millimeter Array, a network of radio telescope dishes in Chile's Atacama Desert, can observe Neptune in sub-millimeter and millimeter wavelengths, probing the thermal emission from the planet at different atmospheric depths. This allows scientists to map temperature as a function of depth in the atmosphere, complementing the infrared measurements from Webb and providing a more complete picture of how energy is distributed vertically. What all of these observing campaigns share is a sense of accumulating evidence from a planet that is changing on observable timescales. When Voyager 2 flew through the Neptune system in 1989, it provided a baseline measurement against which all subsequent observations can be compared. What has accumulated in the decades since is a record of change. Storms appearing and disappearing, seasons shifting, the southern hemisphere brightening, the upper atmosphere cooling, auroras detected for the first time. Each observation adds another data point in what is becoming a time series of Neptune's atmospheric and magnetospheric evolution. Understanding what drives that evolution requires not just more observations of Neptune, but also better theoretical models of how ice giant atmospheres and magnetic fields work. Much of the theoretical framework used to interpret Neptune observations was developed from studies of Jupiter and Saturn, the gas giants, which differ significantly from the ice giants in interior composition and structure. The electrical conductivity of water-ammonia mixtures under the high pressures found in ice giant interiors is different from the hydrogen metallic layers inside Jupiter and Saturn, which means the dynamics of magnetic field generation are likely different as well. Laboratory experiments using high-powered lasers and shock compression techniques have been testing the behavior of water-ammonia-methane mixtures at pressures comparable to those inside ice giants. These experiments have produced data on conductivity, equation of state, and phase behavior that are being incorporated into improved interior models. The results suggest that the boundary between the conducting fluid mantle and the outer atmosphere of an ice giant may be less sharply defined than in a gas giant, and that the magnetic field generation may occur over a broader range of depths, which would produce the asymmetric, multipole magnetic fields observed at both Uranus and Neptune. Understanding these interior processes is relevant not just to Neptune, but to the entire population of sub-Neptune and Neptune-sized worlds in the galaxy. If Neptune-class planets have multipolar, asymmetric magnetic fields as a class property, as current models suggest, then their magnetospheres and their interaction with stellar winds and radiation are very different from those of planets with dipolar magnetic fields, like Earth or Jupiter. This affects how their atmospheres are eroded by stellar radiation over time, which in turn affects whether they can maintain atmospheres capable of supporting habitability over geological timescales. These questions place Neptune at the intersection of solar system science and exoplanet science. What happens inside Neptune, how its magnetic field is generated, how its atmosphere interacts with the solar wind, all of these have direct implications for understanding the physics of the most common type of large planet in the galaxy. A mission to Neptune would be doing science not just about one distant planet in our own solar system, but about a class of worlds that may be inhabited or potentially habitable throughout the observable universe. The particular status of Neptune as the outermost planet also gives it a special place in the history of planetary discovery. Every planet inside Neptune's orbit was known to ancient astronomers who noticed the wandering points of light against the background of stars. Mercury, Venus, Mars, Jupiter, and Saturn were known to every civilization on Earth that practiced systematic astronomy. Uranus was discovered in 1781 by the arrival of the first telescopes powerful enough to reveal its disk. And then, at the very edge of the known solar system, Neptune was found not by looking through a telescope, but by thinking through the mathematics of gravitational physics, a discovery that demonstrated, for the first time, that the laws of physics could be used to predict the existence of unknown objects and specify their locations in the sky. That discovery changed how scientists thought about the solar system and about the reach of physical law. If a planet could be found through calculation, then the same approach might find other things, and indeed, the same mathematical method was applied in the early 20th century in the search for a planet beyond Neptune, which led to the discovery of Pluto in 1930. Pluto turned out not to be the gravitational perturber that some astronomers had predicted, but the search itself had extended the mathematical approach that began with Neptune to the far reaches of the solar system. Leverrier, the mathematician who predicted Neptune's location, went on to apply the same technique to the orbit of Mercury, where a small but persistent anomaly in the planet's precession could not be explained by the gravitational effects of the known planets. He proposed that an unseen planet, which he named Vulcan, must exist inside Mercury's orbit. Searches were conducted, and some observers reported seeing objects cross the solar disk that they thought might be Vulcan, but the planet was never confirmed. The mystery of Mercury's orbital anomaly persisted for decades, until Albert Einstein's general theory of relativity, published in 1915, provided an explanation that required no new planet at all. The anomaly was a consequence of the curvature of space-time near a massive object like the Sunday. Mercury's orbit, being the closest of the planets, showed the effect most clearly. The story of Neptune's discovery is therefore embedded in a larger story about how science progresses. A mathematical prediction based on observed anomalies led to the discovery of a new planet. The same mathematical approach applied to another anomaly led instead to a failure. But the failure, decades later, led to a new and deeper theory of gravity. Both outcomes advanced the understanding of the solar system, just by different paths. Neptune itself has continued to reward investigation at every stage. The James Webb Space Telescope's observations of 2025 are the most recent chapter in that story, but they are not the last. Science rarely reaches a final answer. It reaches new questions, which require new observations, which generate new data, which produce new understanding, which raises new questions. Neptune has been generating new questions since the night of September 23, 1846, when Johann Galle first centered it in his eyepiece and confirmed that mathematics could reach out across 4.5 billion kilometers of empty space and touch a world that no human eye had ever seen. That world is still there, still generating questions. Its storms still form and vanish. Its rings still carry unexplained arcs of concentrated material. Its captured moon still erupts cryovolcanically, renewing a surface that may cover a liquid ocean. Its thermosphere is cooling in ways that are not fully understood. And in March of 2025, it revealed its auroras for the first time, dim mid-latitude halos, recorded in infrared light by the most powerful space telescope ever built, reaching across 4.5 billion kilometers to answer a question that scientists had been holding for more than 30 years, and in the process raising several new ones. That is what Neptune does. It is the planet that keeps producing surprises. The final planet, the most distant, the hardest to reach, the least visited, and the most mysterious. And it is not finished yet. There is a concept in planetary science called comparative planetology. The idea that studying different planets in the solar system alongside each other yields insights that studying any one planet in isolation cannot provide. The value of the concept is that the solar system, having formed from a single disk of material around the young sun, represents a natural experiment in which the same starting ingredients produced a remarkable variety of outcomes. By comparing those outcomes, scientists can identify which factors' initial mass, distance from the sun, internal heat, presence or absence of large moons, impact history are responsible for which observed properties. Neptune occupies a unique position in the comparative planetology framework. It is one of only 2 known ice giants in our solar system, and its companion Uranus is so different from it in terms of current activity levels that the pair presents an immediate and fascinating puzzle. 2 planets of very similar composition, very similar mass, very similar distance from the sun, yet one is nearly geologically dead, and the other is one of the most meteorologically active planets in the solar system. Understanding that difference requires understanding both planets deeply, and currently neither is understood as well as Jupiter, Saturn, or even Mars. The ice giants also represent a transitional class between the rocky planets and the gas giants. Neptune is large enough to have retained a thick atmosphere of hydrogen and helium, but not large enough to have accreted the enormous quantity of gas that makes Jupiter and Saturn so massive. Neptune's mass, just over 17 times Earth's mass, sits at or near the theoretical threshold above which planetary atmospheres begin the runaway accretion of gas that turns a protoplanet into a gas giant. Understanding exactly where that threshold is, and what physical processes determine it, is one of the central questions in the theory of planet formation. The composition of Neptune's interior is central to this question. If the icy mantle of Neptune contains water in a partially dissociated ionic state, the resulting electrical conductivity could support the generation of a complex magnetic field through a dynamo process. Laboratory experiments have confirmed that water becomes electrically conductive at pressures of a few megabars, which corresponds to depths of roughly 10,000 to 20,000 kilometers below Neptune's visible atmosphere. In this regime, the water molecules partially dissociate into hydrogen and oxygen ions that can carry electrical current, and the convective motion of this conducting fluid in Neptune's rotating interior could generate and sustain the tilted, multipolar magnetic field that Voyager 2 measured. This picture is consistent with Neptune's observations, but has not been directly confirmed. An orbiter with a precise magnetometer could map Neptune's magnetic field at multiple points along the orbit, tracking how the field varies with latitude and local time and how it evolves over the duration of the mission. Comparing those measurements to computer simulations of dynamo processes in conductive water-ammonia mixtures would either confirm the model or reveal new features requiring explanation. The same kind of detailed magnetic mapping has been done for Jupiter by the Juno mission, producing a detailed 3-dimensional map of Jupiter's internal magnetic field that revealed more small-scale structure near the surface than any model had predicted. Similar mapping at Neptune would almost certainly produce comparably surprising results, given how different Neptune's interior structure is from Jupiter's. The interaction between Neptune's magnetic field and the solar wind, the continuous stream of charged particles flowing outward from the sun, creates a magnetosphere that is unlike any other in the solar system. Jupiter's magnetosphere is enormous, extending outward for millions of kilometers and containing powerful radiation belts that are intense enough to damage spacecraft electronics. Saturn's magnetosphere is nearly symmetric around the planet. Earth's magnetosphere is compressed on the sunward side and stretched into a long tail on the night side. Uranus's and Neptune's magnetospheres, with their extreme tilt relative to the rotational axis, rotate with the planet in a way that causes them to wobble dramatically, alternately presenting their open and closed field regions to the solar wind over the course of a single planetary day. Neptune's day is approximately 16 hours and 6 minutes long. As Neptune rotates, its tilted magnetic field sweeps through space like a wobbling top, alternately opening and closing paths for solar wind particles to penetrate to the planet. This creates a highly dynamic interaction that is very different from the steady state of Jupiter's or Saturn's magnetospheres. Understanding this interaction requires continuous measurement over at least several planetary rotation periods, which a flyby mission cannot provide. There are also practical reasons why understanding Neptune's radiation environment matters. Any future mission to Neptune, whether an orbiter, an atmospheric probe, or a lander on Triton, will have to operate in whatever radiation field surrounds the planet. Unlike Jupiter, where intense radiation belts are a serious engineering challenge that limits how close spacecraft can safely orbit, Neptune's radiation environment is thought to be far less intense. But without in situ measurement, the details remain uncertain. Planning the engineering of a long-duration orbiter requires knowing what particle fluxes and radiation doses the spacecraft will encounter at different orbital distances. For a mission to Triton, understanding the radiation environment is particularly important. If the scientific goal includes searching for surface chemistry related to potential habitability, detecting complex organic molecules, mapping the distribution of tholins, identifying freshly erupted cryovolcanic material, the instruments designed to do that work will need to operate in whatever particle environment exists near Triton's surface. Getting that design right requires the kind of detailed environmental characterization that only an in situ measurement campaign can provide. The question of Triton's origin continues to be refined by observations of the Kuiper Belt and the comparison of Kuiper Belt objects to Triton. Since the discovery of Pluto in 1930, astronomers gradually accumulated evidence that the outer solar system beyond Neptune contains a vast reservoir of icy bodies extending from about 30 astronomical units out to perhaps 50 or 60 astronomical units from the Sunday. This region, the Kuiper Belt, was first directly confirmed in 1992 when astronomers David Jewett and Jane Liu discovered the first trans-Neptunian object after Pluto. Since then, thousands of Kuiper Belt objects have been discovered, ranging from small irregular chunks to large dwarf planets rivaling or exceeding Pluto in size. The largest confirmed Kuiper Belt objects include Eris, which is slightly more massive than Pluto, Makemake, Haumea, and Quaoar, among others. Studies of their compositions, densities, and orbital properties have revealed that Kuiper Belt objects formed in the cold outer disk of the early solar system and have largely been preserved in that cold state for the 4.5 billion years since. Triton's composition, measured by Voyager 2 and confirmed by comparison with New Horizons data from Pluto, matches the Kuiper Belt archetype closely. Nitrogen ice on the surface, water ice in the deeper layers, carbon dioxide mixed in, tholins from ultraviolet processing of methane. A relatively high density consistent with a rock and ice composition rather than a pure ice body. All of these features are shared between Triton and the large Kuiper Belt objects. The capture scenario for Triton raises interesting questions about the history of the Kuiper Belt itself. If Triton was once a binary Kuiper Belt object that was captured by Neptune, then many other Kuiper Belt objects may once have had binary companions that were disrupted by close encounters with the giant planets, as those planets migrated outward. The distribution of Kuiper Belt objects their orbital resonances with Neptune. Their inclinations, their eccentricities carries the imprint of Neptune's outward migration through what was once a much more densely populated region. Computer simulations of the early solar system, including the Grand-Tack model and the NICE model and their successors, suggest that the Kuiper Belt was once perhaps 100 times more massive than it is today. The outward migration of Neptune swept through this primordial disk, capturing some objects into resonances, scattering others onto highly eccentric orbits, and ejecting still others entirely from the solar system. The survivors that remain in the Kuiper Belt today represent a fraction of what was once there, a depleted remnant of the original outer disk, shaped by billions of years of gravitational sculpting by Neptune. The Late Heavy Bombardment, a period roughly 4 billion years ago when the inner solar system experienced a high rate of large impacts, may have been triggered by this migration. If the giant planets shifted in their orbits on a timescale of tens of millions of years rather than gradually over hundreds of millions, the disruption of the Kuiper Belt could have sent a shower of icy bodies on trajectories that crossed the orbits of the terrestrial planets, producing the cratered surfaces observed on the Moon, Mars, and Mercury. Neptune's migration may therefore have been not just an event in the history of the outer solar system, but a defining event in the history of the inner solar system, and possibly in the history of life on Earth. Water on Earth is thought to have been delivered in part by impacts from icy bodies originating in the outer solar system during and after the planet's formation. The exact fraction of Earth's water that came from Kuiper Belt objects versus asteroid belt objects versus material accreted directly during formation is still debated. But the contribution from outer solar system icy bodies is considered significant. Neptune's role in shaping the Kuiper Belt and directing objects from it into the inner solar system connects the story of the most distant planet to the story of water on Earth, and therefore potentially to the origin of life on Earth. This perspective gives Neptune a significance that extends well beyond its status as the eighth and outermost planet. It is not merely the most remote planet, it is the gravitational architect of the outer solar system, the shepherd of the Kuiper Belt, the captor of a dwarf planet, and a key player in the history of the inner solar system. Understanding it fully requires understanding it not just as a static object, but as a dynamical agent that has shaped the solar system over billions of years. The fact that we know so little about it given all of this significance makes the case for a dedicated mission compelling. But missions to the outer solar system require patience. The journey itself takes over a decade. The data collection requires years. The analysis and publication of results takes additional years after that. A researcher who begins their career working on a Neptune mission concept today might not see the orbital insertion occur until they are decades older. This is the nature of outer solar system exploration, and it requires a sustained institutional commitment that transcends the careers of any individual scientist. The history of Cassini at Saturn illustrates this point well. Cassini was conceived in the late 1980s, launched in 1997, and arrived at Saturn in 2004. The mission continued until 2017, when the spacecraft was deliberately steered into Saturn's atmosphere to prevent any possibility of contaminating Enceladus or Titan. Over its 13 years in orbit, Cassini transformed the scientific understanding of Saturn, its rings, and its moons more completely than any other mission to the outer solar system. The scientists who contributed the most to that mission's legacy were often not the same people who first proposed it. They were the graduate students and early career researchers of the late 90s and 2000s who grew with the mission as it produced its data. A Neptune mission would follow a similar arc. The science questions being defined today about thermospheric cooling, about ring arc stability, about Triton's subsurface ocean, about magnetic field generation will be answered by instruments and data analysis techniques that are still being developed, interpreted by scientists who are still in graduate school or have not yet begun their careers. In the meantime, the tools available for remote sensing of Neptune continue to improve. The extremely large telescope, under construction in Chile, will have a mirror over 39 meters in diameter when complete, making it by far the largest optical and infrared telescope ever built on Earth. Its adaptive optic system will be capable of correcting atmospheric blurring with unprecedented precision, potentially allowing it to resolve features in Neptune's cloud layers that currently require space-based observations. Combined with Webb and with future space telescopes, the extremely large telescope will extend the monitoring campaign that has been tracking Neptune's atmospheric evolution since Voyager 2. Next-generation radio telescope arrays are also being planned and built, with capabilities that will allow more detailed mapping of Neptune's microwave emission, which probes deeper levels of the atmosphere than infrared observations. Understanding the deep atmospheric structure, how temperature and composition change with depth below the visible cloud layer is essential for interpreting the convective processes that drive the surface weather. The time between now and the arrival of a dedicated Neptune orbiter, if such a mission is approved and launched, will be filled with observations like these, accumulating data points and building the scientific context that will make the orbital mission most productive when it eventually occurs. Every new Webb observation of Neptune's auroras, every tracking of a Neptunian storm by ground-based adaptive optics, every measurement of the ring arcs by a sub-millimeter observatory adds to a dataset that a future orbiter will be able to compare against its own measurements, extending the temporal baseline of the observations and enabling studies of how Neptune changes on timescales spanning decades rather than years. The 2025 Webb observations are therefore not an isolated result. They are a data point in an accumulating record. The temperature reading is now being compared to Voyager 2's measurement from 36 years earlier, to Hubble measurements taken in intervening years, and to ground-based spectroscopic measurements made over the same period. What emerges from that comparison is a timeline of how Neptune's upper atmosphere has evolved, which is the kind of time series data that scientific models can test and constrain. Neptune, at the edge of our solar system, connects every timescale in planetary science. Its formation 4.5 billion years ago shaped the distribution of materials in the outer solar system. Its outward migration billions of years ago sent objects into the inner solar system and captured Triton. Its ongoing internal heat drives weather on timescales of years. Its seasons evolve on timescales of decades. Its upper atmosphere has cooled on timescales of decades to possibly a century. Its ring arcs have been stable for at least 40 years. And the James Webb Space Telescope observed its auroras for the first time in 2025, adding a new observational milestone to a story that began on September 23, 1846. Each of those timescales connects to a different scientific question, and each scientific question connects to a broader context: the formation of solar systems, the distribution of water in the universe, the conditions for habitability on ocean worlds, the physics of magnetic field generation in conducting fluids, the dynamics of ring systems, the evolution of ice giant atmospheres over planetary and stellar timescales. Neptune is not just one planet. It is a window into all of these questions at once. The final planet may be the most distant, but in terms of what it can teach about the solar system and the broader universe, it is anything but peripheral. One aspect of Neptune's story that does not receive enough attention in popular science is the sheer scale of the ignorance we are dealing with. When scientists talk about Neptune's interior, they are largely working from inference and analogy, rather than direct measurement. The interior models are built from equations of state mathematical descriptions of how materials behave under pressure and temperature, derived from laboratory experiments conducted at pressures and temperatures that approximate, but do not exactly replicate, the conditions inside Neptune. The models are then constrained by the few things we can actually measure from a distance: Neptune's total mass, its gravitational field, its overall radius, its rotation rate, and its luminosity. From those few numbers, and from the physics of how materials behave under extreme conditions, scientists construct pictures of what Neptune looks like on the inside. But the number of possible interior configurations that are consistent with those observed quantities is quite large. Different assumptions about where exactly the boundary between the icy mantle and the gaseous atmosphere lies, or about the composition of the core, or about how heat is distributed through the interior, can all produce models that fit the observational constraints equally well, while making very different predictions about what is actually happening inside the planet. This is the standard situation in planetary interior science, but it is worth emphasizing how much deeper the uncertainty runs for Neptune than for the planets we have studied more closely. For Jupiter, the Juno mission has been measuring the gravitational field with extraordinary precision, and those measurements, combined with seismological techniques applied to Jovian atmospheric oscillations, are beginning to constrain interior models in ways that rule out previously plausible configurations. For Saturn, Cassini performed a series of ring-grazing orbits during its final months that measured the gravitational field in unprecedented detail, and analyses of ring seismology waves, driven by Saturn's internal oscillations, have produced independent constraints on the interior structure. For Neptune, there is no such high-resolution gravitational mapping. Voyager 2 measured the gravitational field from a single trajectory, which provides only a limited number of the spherical harmonic coefficients that describe the three-dimensional shape of the gravitational potential. An orbiter spending years in the Neptune system and performing multiple flybys at different inclinations and distances could map the gravitational field with the same level of precision that Juno has achieved at Jupiter, dramatically narrowing the range of plausible interior models. This would have direct implications for understanding the diamond rain hypothesis. If diamonds do form in Neptune's interior and migrate through the planet, they would affect the density distribution in ways that could leave a signature in the gravitational field. If the icy mantle has distinct compositional layers rather than being a uniform fluid, those layers would also affect the gravitational field in characteristic ways. Reading those signatures requires the kind of precise, long-duration gravitational measurements that only an orbital mission can provide. The diamond rain hypothesis itself is a remarkable scientific prediction that illustrates how planetary science combines laboratory physics with astronomical observation. The idea that carbon atoms deep inside Neptune and Uranus might be subjected to pressures extreme enough to crystallize into diamonds was first seriously proposed in the 1990s when calculations showed that the diamonds' pressure and temperature conditions inside the ice giants fell in a range where carbon could be in its solid diamond phase rather than as part of hydrocarbon molecules or as graphite. The challenge in testing this hypothesis is that the pressures required tens to hundreds of millions of atmospheres are extremely difficult to achieve in a laboratory setting on Earth. The primary tools for reaching such pressures are laser-driven shock experiments, in which powerful laser pulses compress a material to extreme densities and pressures for fractions of a nanosecond, and static compression experiments using diamond anvil cells, which squeeze a small sample between two diamond faces to reach very high pressures. Both methods have limitations in terms of the range of pressures and temperatures they can achieve simultaneously, and in terms of how long the sample can be held at the target conditions. Experiments conducted in the 2010s at laser facilities, including the National Ignition Facility in Livermore, California, and the LINAC Coherent Light Source at the SLAC National Accelerator Laboratory, directly measured the behavior of polystyrene, a hydrocarbon that contains carbon and hydrogen in ratios similar to the hydrocarbon mixture found inside ice giants under shock compression to pressures of several million atmospheres. The results showed that under these conditions, the carbon atoms do indeed separate from the hydrogen atoms and form small diamond crystals. The diamonds formed in nanoseconds and were detected by X-ray scattering measurements taken simultaneously with the shock compression. These experiments provided direct laboratory evidence that diamond formation can occur under the pressure and temperature conditions expected inside Neptune and Uranus. They did not measure what happens to those diamonds once formed, whether they dissolve back into the surrounding fluid, whether they continue to grow, or whether they sink toward the core under gravity. But the evidence that the initial diamond formation process is physically real substantially increased scientific confidence in the diamond rain hypothesis. Subsequent modeling work has explored the implications of diamond formation and migration for the thermal evolution of ice giants. If diamonds form and sink toward the core, they carry latent heat with them as they travel through the mantle, and the release of that heat as they dissolve or settle into the core could contribute to the excess heat radiated by Neptune. This would be a distinctive mechanism for internal heat generation that does not apply to gas giants like Jupiter, which lack the high abundance of carbon-bearing compounds needed to produce significant quantities of diamond. If this mechanism is operating inside Neptune, it could help explain why Neptune radiates more excess heat than Uranus, though this is just one of several competing hypotheses for the heat flux asymmetry between the two ice giants. The chemistry of Neptune's deep interior is also relevant to understanding the planet's atmospheric composition. Elements that are locked up in high-pressure compounds deep in the interior cannot easily reach the surface. If carbon is forming diamonds deep in the mantle, then some of the carbon that would otherwise contribute to the methane abundance in the atmosphere is being sequestered in the interior. This could affect the carbon-to-hydrogen ratio in the atmosphere, which is one of the quantities astronomers measure remotely to infer the composition of the interior. Getting those inferences right requires knowing what chemical transformations are occurring at depth, which is precisely what the diamond rain work is trying to establish. The nitrogen chemistry in Neptune's atmosphere is another area of active investigation. Neptune's upper atmosphere shows spectroscopic signatures of molecules, including nitriles, compounds containing carbon-nitrogen triple bonds that are produced when methane and nitrogen react in the presence of ultraviolet radiation or energetic particles from aurora. These nitriles are organic molecules, part of the same family of compounds found in Titan's atmosphere and on Triton's surface, and their presence in Neptune's atmosphere adds to the picture of a chemically active outer solar system where the organic chemistry of life's building blocks is widespread. Understanding how these molecules form, how they are distributed vertically through Neptune's atmosphere, and how they interact with the meteorological processes in the cloud layers requires detailed chemical measurements at multiple altitudes. An atmospheric probe could sample the composition as it descended, directly measuring the abundances of various species at each pressure level and building up a profile that would constrain models of atmospheric chemistry and dynamics. The cloud structure of Neptune's atmosphere is another largely unexplored topic. Visible images show the bright cloud features that mark the tops of active weather systems, and spectroscopic observations give some information about the chemical composition of those features. But the detailed vertical structure, what kinds of clouds form at what altitudes, what their particle sizes and shapes are, how they evolve, is essentially unknown. Comparison with Jupiter and Saturn, where detailed cloud structure data from Galileo and Cassini is available, suggests that Neptune should have multiple cloud layers at different altitudes corresponding to the condensation levels of different gases. But the direct observational evidence for this at Neptune is sparse. One of the intriguing aspects of Neptune's cloud structure is the relatively higher abundance of methane compared to Uranus. Both planets have methane in their atmospheres, and methane gives them their blue color. But Neptune appears a darker, deeper blue than Uranus, a difference that has been measured more precisely in recent years, and is thought to reflect differences in the concentration of an absorbing haze component in the atmosphere above the methane layer. The source and chemistry of this haze, which may be related to the same nitrile and tholin chemistry found on Triton, is an active area of study. Identifying whether the haze is different between the two planets in ways that correlate with their different internal heat output, or with some other physical parameter, would be a step toward understanding the ice giant color mystery. The question of what drives the color difference between Uranus and Neptune connects to a broader puzzle about the two planets. They are so similar in so many respects: comparable mass, comparable radius, similar chemical composition, similar distance from the sun, that their differences are scientifically valuable as diagnostics. Any property that differs between the two planets represents a clue about which factors are most important in determining that property. The color difference, the internal heat difference, the wind speed difference, the storm activity difference. Each of these points to something in the formation history, the impact record, or the internal dynamics of the two planets that set them on different evolutionary paths. The most discussed explanation for many of these differences is the hypothetical large impact on Uranus. If Uranus was struck by an Earth-sized body during the late stages of solar system formation, the impact could have driven out much of its primordial heat, explaining the low current heat flux. It could have tipped the rotation axis to its current extreme value of nearly 98 degrees. It might have generated enough mixing in the atmosphere to smooth out differences between compositional layers, changing the haze structure and therefore the color. The impact might have disrupted a previous moon system and generated the current ring and moon configuration from the debris. None of this is proven. The evidence for a large impact on Uranus is circumstantial. The extreme axial tilt, the low heat flux, the strange configuration of the moons and rings. But it is consistent with the hypothesis and is taken seriously by most planetary scientists working on the ice giant problem. If Uranus did suffer such an impact and Neptune did not, then the comparison between the two planets is essentially a comparison between a planet that experienced a major collision and one that did not, a controlled experiment of sorts that is present in our own solar system and waiting to be read. Reading it requires detailed data from both planets. Uranus has been identified as the highest priority target for the next large NASA planetary mission in the most recent Planetary Science Decadal Survey, and a mission concept called the Uranus Orbiter and Probe is being developed. If that mission proceeds, it will provide the kind of detailed compositional, meteorological, and magnetic data for Uranus that is needed to make the comparison with Neptune meaningful. But the value of that comparison depends on having comparably detailed data from Neptune as well. A Uranus mission without a corresponding Neptune mission leaves the comparison incomplete. Some mission designers have considered whether a single mission could visit both ice giants, using gravitational assists at one to reach the other. The geometry of the solar system makes this challenging. The planets' positions relative to each other vary over time, and the trajectories that allow efficient travel to one are not always compatible with onward travel to the other. But studies have shown that certain launch windows in the late 2030s to 2040s would allow spacecraft to visit both Uranus and Neptune on the same mission using Jupiter gravity assists, though the mission design would have to balance the competing requirements for observations at both planets. This idea of a dual ice giant mission has generated interest in the planetary science community, but has not been formally proposed as a mission concept. The more practical near-term path appears to be separate, dedicated missions to each planet, with a Uranus orbiter and probe expected to be developed in the late 2020s and early 2030s for a potential launch in the late 2030s, and a Neptune mission potentially following in the next decadal cycle. In the meantime, the observations continue. Webb's 2025 images of Neptune's auroras and thermosphere have been shared with the scientific community, and the analysis is ongoing. Modeling groups are incorporating the new temperature constraints into updated atmospheric models, testing different hypotheses for what could drive the cooling, and whether the detected change is part of a long-term trend or a transient fluctuation. The aurora images are being analyzed to characterize the latitude distribution and intensity of the emission, compare it to theoretical predictions based on the Voyager 2 magnetic field map, and look for spatial structure that might reveal details about how particles enter the magnetosphere. Papers will be published over the coming years drawing on this data, and each paper will build on previous work and contribute to the cumulative understanding of Neptune that is slowly, observation by observation, becoming more complete. The pace is slow by human standards, decades between key milestones. But it is the pace at which outer solar system science necessarily moves, given the distances and timescales involved. What is remarkable is that humans have been accumulating this knowledge for only 180 years, beginning from the night of September 23, 1846, when a planet that had never been seen before was confirmed to exist at exactly the location that mathematics had predicted. In those 180 years, the entire orbit of Neptune has not yet completed even once since its discovery. One full Neptunian year has elapsed since discovery, lasting 165 Earth years, ending only in 2011. We are now in the second Neptunian year of the post-discovery era. The planet has completed one and a small fraction of its orbit since it was first found. In that time, we have gone from knowing Neptune as a faint dot in a telescope to knowing it has 5 named rings, 14 known moons, supersonic winds, diamond rain, a tilted magnetic field generating mid-latitude auroras, a captured dwarf planet moon with a subsurface ocean and active cryovolcanoes, seasons 40 Earth years long, and a thermosphere that has been cooling for at least 3 decades. All of that from one spacecraft flyby, occasional telescope observations, and 2 observations by the James Webb Space Telescope in its early years of operation. What the next 180 years will reveal, especially if they include an orbital mission, is genuinely unknown. And that unknowability, that sense that the most distant planets still hold secrets substantial enough to reshape understanding, is exactly what continues to make Neptune one of the most compelling objects in the solar system to study. The auroras that Webb photographed in 2025 were there all along. Neptune was generating them continuously, driven by particles spiraling along field lines that Voyager 2 measured in 1989. For 36 years, those auroras glowed in the infrared above the mid-latitudes of the most distant planet, visible to any instrument sensitive enough to detect them from 4.5 billion kilometers away. The James Webb Space Telescope was the first instrument sensitive enough to capture them. What else is out there? Similarly waiting, generating its signal continuously, at the edge of detection, until the right instrument points in the right direction. Neptune does not keep its secrets because it is hiding them. It keeps them because reaching it is so difficult, and because the signals it sends are so faint by the time they cross 4.5 billion kilometers of empty space. Every improvement in our ability to detect and interpret those faint signals is a step toward understanding a world that is, in almost every respect, unlike anything in the inner solar system, and at the same time, more representative of the most common type of large planet in the galaxy than anything closer to home. The final planet, the furthest away, the last to be visited. And still, after almost 2 centuries of study, the one with the most still to say. The rings of Neptune deserve more detailed attention than they typically receive in discussions of the outer solar system. While Saturn's rings are the most famous visible through a small backyard telescope and stretching over 280,000 kilometers from the planet's center, and Uranus's rings were famously discovered in 1977 when they were observed blocking the light of a background star, Neptune's rings have remained one of the most understudied ring systems in the solar system. The reason is the same as for everything else about Neptune. It is simply too far away and has been visited too infrequently for detailed study. What makes Neptune's ring system particularly interesting scientifically is the Adam's ring and its arcs. The other rings, Gal, Leverrier, Lassell, and Arago, are more typical of faint planetary ring systems, broad, diffuse, composed of small dark particles that reflect very little sunlight. The Adam's ring is different. It is narrow, relatively bright, slightly inclined relative to Neptune's equatorial plane, and contains within it several discrete concentrations of material, the arcs that are named Courage, Liberté, Eaglite 1, Eaglite 2, and Fraternite. These arcs occupy a small fraction of the total circumference of the Adam's ring. Rather than being spread uniformly around the orbit, the material in the arcs is clumped into dense concentrations that occupy perhaps 40 degrees of arc in total out of the full 360 degrees of the ring. The arcs appear bright in images because the concentrated material there reflects significantly more light than the diffuse background ring. What prevents the arcs from spreading out uniformly around the ring? This is the question that has challenged theorists since the arcs were first detected in ground-based observations in the early 1980s. In a ring with no other forces acting on it, differential orbital motion would spread any concentration of material uniformly around the orbit on timescales of decades to centuries far shorter than the time since the arcs were first observed. Something must be actively confining the material. The leading mechanism proposed is a mean motion resonance with one of Neptune's small inner moons. The moon Galatea, which orbits just inside the Adam's ring, completes exactly 42 orbits for every 43 orbits completed by ring particles in the arcs. This 42 to 43 resonance means that a ring particle in the arc experiences a repeated gravitational nudge from Galatea at the same phase of its orbit each cycle. In principle, this can create a pattern of stable and unstable orbital positions within the ring potential wells in orbital phase space that could trap material and prevent it from spreading. Whether this mechanism is sufficient to explain the observed arcs has been debated for decades. Theoretical analyses show that the Galatea resonance can confine material azimuthally in orbital phase, but there are difficulties with the model, particularly in explaining the specific sizes, positions, and brightness contrasts of the observed arcs. Some studies have suggested that additional shepherd moons, not yet discovered, might be needed to fully explain the arc structure. Others have proposed that the arcs are not truly stable, but are slowly evolving and will eventually disappear on a timescale of perhaps thousands of years. Ground-based observations taken over the past few decades have provided some evidence that the arcs are indeed changing slowly. Observations taken in the 2000s showed that the positions of the arcs relative to the Galatea resonance had shifted compared to Voyager 2's images from 1989. The Liberté arc, in particular, appeared to have faded significantly between the Voyager images and more recent ground-based observations. If this trend continues, Liberté may be in the process of dispersing, which would be a direct observation of a planetary ring arc evolving on human timescales. If the arcs are indeed transient features maintained temporarily by resonance forces, but gradually leaking material into the broader ring, then the question becomes, how old are the arcs, and what created them in the first place? One hypothesis is that a ring arc forms when a larger body, a small moonlet embedded in the ring, is disrupted by a collision or by tidal forces from Neptune, and the debris is initially concentrated in a small arc before slowly spreading. If Galatea's resonance then traps the concentrated debris in a stable configuration, the arc could persist for thousands to tens of thousands of years before finally dispersing. This scenario connects to broader questions about how ring systems form and evolve. Saturn's rings are thought to be geologically young, perhaps only a few 100 million years old, formed from the disruption of a former moon or from the tidal disruption of a comet that came too close. Neptune's ring arcs may represent a similar process on a smaller scale, a recent collision or disruption event whose debris is still in the process of spreading out and joining the broader ring system. Observing the evolution of the arcs over the coming decades with increasingly precise instruments may allow scientists to measure the rate of spreading directly and work backward to estimate when the arcs formed. A dedicated Neptune orbiter would be invaluable for this purpose. By imaging the rings from multiple angles, at high resolution, and at multiple epochs spread over years, it could map the three-dimensional structure of the Adam's ring arcs in detail, measuring the radial and vertical extent of the arcs as well as their azimuthal position and brightness. It could search for the small embedded moonlets that theoretical models predict should be present in or near the arcs, acting as local sources of material. And it could measure how the arc positions change relative to the Galatea resonance over the course of the mission, testing whether the resonance confinement model correctly predicts the observed dynamics. The gravitational interaction between Neptune's rings and moons also provides a probe of the interior of the planet. Certain oscillations of Neptune's atmosphere pressure waves propagating around the planet can interact resonantly with ring particles, causing them to bunch up into ring structures whose spacing and brightness encode information about the frequency of the atmospheric oscillations. This technique, called ring seismology, was applied spectacularly to Saturn's rings using Cassini data, revealing features in Saturn's rings that correspond to specific normal mode oscillations of the planet's interior. The same technique could in principle be applied to Neptune's rings with sufficient observational data. To do ring seismology of Neptune requires images of the rings at high resolution and high signal-to-noise ratio taken over a long enough baseline to detect the very fine-scale density waves that atmospheric oscillations produce. From Earth's distance, even with the largest existing telescopes, achieving the required spatial resolution is extremely challenging. From an orbiting spacecraft, imaging the rings from inside the ring system itself, or from a few thousand kilometers away, the required detail is straightforwardly achievable. The scientific return from ring seismology would be direct constraints on Neptune's interior oscillation frequencies, which are sensitive to the density and sound speed profile as a function of depth inside the planet. Combined with precise gravitational mapping, compositional measurements from spectroscopy, and thermal emission data from infrared observations, Ring seismology data would allow the construction of detailed interior models that are tightly constrained by multiple, independent, observational datasets. This multi-technique approach is exactly what has made Jupiter and Saturn the best understood of the giant planets, and applying it to Neptune would produce a comparable step change in understanding. Triton's orbital dynamics also carry information about Neptune's interior. As Triton orbits Neptune on its retrograde inclined path, tidal forces between Triton and Neptune cause Triton's orbit to slowly decay. Unlike our moon, which is gradually moving away from Earth as tidal forces transfer angular momentum outward, Triton is moving closer to Neptune on a very long timescale. This decay is driven by the tidal dissipation, the heating of material inside Neptune, as it is periodically deformed by Triton's gravity. The rate of orbital decay depends on how efficiently Neptune dissipates this tidal energy, which in turn depends on the viscosity and structure of the interior. Measuring the rate at which Triton's orbit is decaying requires tracking Triton's position with high precision over many years. Voyager 2 measured Triton's orbital elements in 1989, providing one data point. Ground-based astrometric observations and Hubble images have contributed additional measurements since then. An orbiter in the Neptune system would dramatically improve the precision of these measurements, determining the tidal decay rate with enough accuracy to constrain the tidal dissipation factor of Neptune's interior, a key parameter in interior models. Eventually, Triton will spiral close enough to Neptune that tidal forces will exceed the self-gravity holding Triton together. The moon will be torn apart, spreading its material into a spectacular ring system around Neptune. The timescale for this to occur is estimated at roughly 3.5 billion years from now, well beyond any human concern. But the process illuminates the dynamic nature of planetary systems. Ring systems, moons, captured objects, resonances, all of these are not static features of a fixed solar system, but are evolving continuously on timescales that range from human observable to geological. The discovery of Hippocamp, the small moon likely chipped from Proteus by a collision, is another example of this dynamism. When Hubble detected Hippocamp in 2013, it became one of the smallest moons ever detected from Earth orbit, just 35 kilometers long. Its close proximity to the much larger Proteus and the heavily cratered state of Proteus's surface suggests that the two objects share a history. A large impactor struck Proteus with enough force to excavate a significant crater and eject debris, and some of that debris coalesced into Hippocamp. The impact that caused this was not from the early solar system, but from a much later time. The crater responsible is one of the largest on Proteus, relative to its size, but it is not as heavily degraded as the oldest craters, suggesting it is geologically recent. This kind of event, a collision energetic enough to produce a detectable moon, is not unique to Neptune's system. Many small moons throughout the solar system are thought to be debris from collisions with larger moons. Phobos and Deimos, the moons of Mars, may have formed from debris ejected by an ancient large impact on Mars itself. Several small moons of Saturn appear to be accretion piles of ring material rather than primordial objects. The processes of moon formation and destruction are ongoing throughout the solar system, occurring at rates low enough that they are rarely observed in action, but high enough that their products, small moons, ring systems, surface craters, are visible everywhere we look. Neptune's moon system is a compressed version of this general story. Triton's retrograde orbit has gradually disrupted whatever moon system existed before its capture, perturbing those original moons into the wide, eccentric, inclined orbits that the outer, irregular moons now follow. The inner regular moons, Proteus and its smaller siblings, are thought to have formed from a disk of debris created by Triton's capture, as the disrupted original moon system was ground down by collisions. Hippocamp is the latest chapter in the ongoing evolution of that inner system, and in roughly 3.5 billion years, when Triton's orbit finally decays to the Roche limit, Neptune will gain a massive ring system as a legacy of the capture event that defined its satellite system. All of this is known at some level of confidence and precision from Voyager 2's brief visit, from ground-based and orbital telescope campaigns, and from the handful of targeted Webb observations. The story is coherent and internally consistent, but the level of detail available is much lower than for any other major planet system. The broad strokes are understood. The details, the precise interior structure, the exact mechanism of ring arc confinement, the current state of Triton's subsurface, the cause of the thermospheric cooling, the structure of the magnetosphere in 3 dimensions remain to be filled in. Those details matter not just because scientists are curious, though of course they are. They matter because each detail is a test of a model, and models that can be tested against Neptune's data will be models that can be applied to exoplanets with more confidence. Every specific quantity measured at Neptune, the atmospheric methane abundance, the tidal dissipation factor, the magnetic dipole tilt, the cloud particle sizes, is a calibration point for theories that are used to interpret observations of planets around other stars, where no direct measurements of any of these quantities are possible. The connection between Neptune and exoplanet science runs deeper than this. Future space telescopes designed to image and characterize Earth-like planets around nearby stars will need to distinguish between different classes of larger planets in the same systems in order to understand the orbital architecture and assess the likelihood of rocky planets being habitable. Neptune-sized planets at various orbital distances from their stars will be among the objects these telescopes need to analyze. The knowledge accumulated from studying Neptune in detail will inform what spectral features to look for, what atmospheric compositions to expect, and how to interpret the observations. This is the long arc of planetary science. Knowledge flows from the specific to the general, from the well-measured to the poorly understood. The reason scientists study Neptune with such care and argue so persistently for missions to this remote and difficult-to-reach planet is that Neptune is not just Neptune. It is the closest representative of the most common class of large planet in the galaxy, a body 4.5 billion kilometers away that nevertheless holds answers relevant to questions being asked about planets orbiting entirely different stars. The auroras captured by Webb in 2025 are a small piece of that larger picture. A glowing mid-latitude halo on the most distant planet, detected in infrared light from the second Lagrange point, confirming theoretical predictions about how a tilted multipolar magnetic field shapes auroral emission on a world with almost no direct sunlight. One observation, one data point in a 36-year gap since the last in situ measurement, and yet informative enough to reshape models, generate new hypotheses, and fuel continued scientific interest in a planet that, despite being the last planet from the Sun, remains far from the last word in planetary science. The story of Neptune is still being written. The most distant planet has not yet told us everything it knows. The name Neptune itself carries history worth reflecting on. When Leverrier's predicted planet was confirmed by Gall in 1846, there was an immediate dispute over what to name it. Leverrier initially wanted to call it Leverrier, after himself, a naming convention that was not unusual at the time, as comets and asteroids were frequently named after their discoverers. The British astronomer John Couch Adams, who had independently made similar calculations to Leverrier, but had not gotten his results acted upon before Gall made the discovery, was involved in a separate priority dispute with Leverrier over who deserved credit for predicting the planet. This dispute, which became known as the Neptune Affair, created significant tension between French and British scientific establishments in the years following the discovery. Eventually, the tradition of naming solar system planets after Roman and Greek deities prevailed. The planet was named Neptune, after the Roman god of the sea, an appropriate name for a deep blue world. The moon discovered a few days after Neptune was named Triton, after the son of Neptune in Roman mythology. The naming of subsequent moons followed the same aquatic mythology theme. Nereid is a sea nymph, Naiad is a water nymph, Galatea is a sea goddess, Despina is a daughter of Poseidon, and so on through the list of Neptune's 14 known moons. The naming convention is one of the small pleasures of planetary nomenclature, connecting the cold mathematics of orbital mechanics to the warm human tradition of mythological storytelling. The moons of Neptune are water deities orbiting a world named after the god of the sea, a poetic coincidence, since the ice giant likely has more water in its interior than any other major body in the inner solar system combined. The question of how much water is in Neptune's interior and in what physical state is one of the more fundamental open questions in ice giant science. Water at the pressures and temperatures found in Neptune's mantle is not liquid in the familiar sense. It is not solid ice either. It exists in a superfluid or ionic state, intermediate between gas and liquid, in which the water molecules partially dissociate, and the resulting ions are mobile enough to conduct electricity, but dense enough to behave more like a liquid than a gas. This state of water is sometimes called a superionic phase, and understanding it is important for understanding both Neptune's interior and its magnetic field generation. Laboratory experiments have studied water under extreme pressures by using laser-driven shock compression and static diamond anvil cell techniques to replicate interior conditions. The results have shown that water under pressures, corresponding to several 100,000 to a few million times atmospheric pressure and temperatures of several thousand degrees Celsius, does enter a superionic phase, in which the oxygen atoms arrange themselves into a crystalline lattice, while the hydrogen atoms move freely through that lattice, like charged particles in a conductor. This ionic hydrogen movement is what makes superionic water electrically conductive, and it is thought to be the primary driver of magnetic field generation in ice giants. The boundary between the superionic mantle and the molecular atmosphere above it may be the location where Neptune's magnetic field is most actively generated. The motion of the superionic water as Neptune rotates, creating a complex pattern of convection in the curved, rotating fluid, produces electrical currents that generate the magnetic field. The asymmetry and tilt of the field are thought to arise from the specific geometry of this convection, which depends on the depth and composition of the superionic layer. Constraining the depth and properties of this layer requires the kind of multi-technique measurements that only an orbital mission can provide. The combination of precise gravitational mapping, long-term magnetic field monitoring, ring seismology constraints on interior oscillation frequencies, and tidal dissipation measurements from Triton's orbital evolution would together paint a detailed picture of the internal structure that is simply not achievable from Earth. The weather of Neptune is another domain that remains largely unexplored at the level of detail achieved for the inner solar system planets. The storms visible in Neptune's cloud layers are dramatic and large, but the atmospheric processes that drive them, the energy transport from the interior, the radiative balance in the stratosphere, the cloud microphysics that determines where condensation occurs, and what particle sizes form are poorly understood. The temperature drop detected by Webb in 2025 adds a new dimension to this puzzle. If the thermosphere is cooling, is the stratosphere also changing? Is the troposphere where the storms form being affected? These questions require measurements at multiple atmospheric levels simultaneously. The vertical temperature profile of Neptune's atmosphere temperature, as a function of altitude from the cloud tops up through the stratosphere and into the thermosphere, is key to understanding the energy budget and the processes that distribute heat through the atmosphere. Voyager 2 provided a single profile at 1 latitude during its brief flyby. Ground-based radio occultation experiments measuring how Neptune's atmosphere refracts radio signals from spacecraft as they pass behind the planet have provided additional profiles at a few other latitudes. But comprehensive global mapping of the temperature profile at multiple latitudes and longitudes, and tracking how those profiles change with season, is far beyond what current remote sensing can provide. An atmospheric probe descending through Neptune's atmosphere would provide a detailed vertical profile, temperature, pressure, chemical composition, and wind speed as continuous functions of altitude from the stratosphere down to wherever the probe survives before being crushed by pressure. The Galileo probe at Jupiter descended to about 23 atmospheres of pressure before going silent. A similar probe at Neptune would penetrate to comparable depths, directly sampling the atmospheric layers that drive the observable weather and providing ground truth for atmospheric models. The timing of such a probe entry would matter. Neptune's atmosphere varies with season and the current period of southern spring, with increasing methane in the stratosphere and brighter southern hemisphere clouds, is a scientifically interesting epoch to sample. A probe entering in the current season would provide data on the atmospheric state during the southward shift of solar forcing, which could be directly compared to models of seasonal atmospheric evolution. Beyond the probe, an orbiter's radio science instruments, which use precise tracking of the spacecraft's radio signals to measure gravitational and atmospheric properties, would provide global atmospheric temperature profiles at multiple latitudes over the course of the mission. Radio occultation profiles taken each time the spacecraft passes behind Neptune as seen from Earth would gradually build up a global map of atmospheric temperature as a function of altitude and latitude, capturing the seasonal evolution over the years of the mission. This is the kind of patient, systematic science that fundamentally changes understanding. Not one dramatic measurement, but hundreds of individual observations accumulating into a coherent global picture. Saturn's atmospheric structure is understood in extraordinary detail because Cassini spent 13 years collecting data from orbit, building up a statistical picture of how the atmosphere varies over space and time. Neptune's atmospheric science is at the level where a single Voyager flyby and occasional telescope observations have produced a sketch informative but coarse-grained, suggestive but incomplete. The patience required for outer solar system science is matched by the patience of the solar system itself. Neptune has been following the same orbit for 4.5 billion years. Its storms have been forming and dissolving for 4.5 billion years. Triton has been spiraling slowly inward for billions of years, and will continue to do so for billions more. The ring arcs may be a few thousand years old, or a few 100,000 either way. They will be there when a spacecraft eventually reaches Neptune, waiting to be studied. That is perhaps the most reassuring aspect of outer solar system science. The objects do not go anywhere. They evolve slowly enough that decades between visits do not significantly degrade the scientific return of future observations. The auroras were there when Voyager 2 flew past in 1989, and they were there in 2025 when Webb finally detected them. They will be there when an orbiter arrives in the 2040s or beyond. The questions that Webb's 2025 observations have raised: why is the thermosphere cooling? How does the auroral structure relate to the magnetic field geometry? What is driving the changes in Neptune's upper atmosphere are questions that will sustain Neptune's science for the next generation of researchers. Graduate students beginning their careers now will spend decades trying to answer them. Some may be part of a Neptune mission team. Others will analyze data from continued Webb observations, from ground-based campaigns, from improved spectroscopic instruments, and from theoretical modeling. The answers will come gradually, as they always do in planetary science, one paper and one observation at a time. What those answers will add up to, eventually, is a complete portrait of Neptune, not just as a static object whose properties can be tabulated, but as a living dynamic system whose atmosphere evolves, whose interior generates heat and magnetic fields, and possibly diamonds, whose moons harbor potential ocean worlds, and whose gravitational influence has shaped the outer solar system over billions of years. That portrait does not yet exist. It is still being assembled, piece by piece, by astronomers and planetary scientists using the best instruments they have available, pointed at a faint blue dot at the edge of the solar system. The James Webb Space Telescope is the latest instrument to contribute to that portrait. Its 2025 images of Neptune's auroras and its measurements of the thermospheric temperature are two new pieces of a puzzle that is 4.5 billion kilometers wide and almost 2 centuries old. They will not be the last pieces. There are more to come, from Webb's future observing campaigns, from ground-based telescopes, from whatever orbital mission eventually reaches Neptune. And each new piece will make the portrait more complete, more accurate, and more surprising, because Neptune, as its history consistently demonstrates, always has one more surprise waiting. The final planet is not finished surprising us. It never has been.